Hello, this is Eric from UNC Charlotte. I am presenting in this video joint work with Maruf Hossain on how vector processing impacts graph partitioning problems. In particular, we look at how to use the recent AVX 512 instruction set to accelerate the Louvain method on Intel CPUs. AVX 512 is a vector instruction set that enables SIMD parallelism inside CPU cores. The vector registers are 512 bit large, which enables to work on 16 32-bit integers at once. We are interested in vectorization for graph problems because vectorization is an increasingly important feature of CPUs. Most CPU architectures can only deliver their maximum performance using vectorization. If one wants to get all the flops from a CPU, one has to use vectorized fused multiply adds, and most processors cannot saturate their memory buses by performing operations on 32-bit at once. Even though AVX 512 can work on 16 SIMD lanes at a time, one does not usually obtain a speedup of 16 because a processor-level resource, such as power or bandwidth, usually saturates before reaching that performance. In many algorithms, like vector sum or matrix multiplication, the code is regular enough for the compiler to leverage vector instructions. However, graph algorithms and most kernels with irregular memory accesses are typically not vectorized by compilers without a significant re-engineering of the algorithm or without manual vectorization. The Louvain method is a popular greedy algorithm to extract communities from large networks by optimizing modularity. The equation presents the gain in modularity when a vertex is moved from a community to a neighboring community. For each vertex, the method finds the destination community with maximum modularity gain among its neighbors, and it moves the vertex to the desirable community if the gain is positive. Sequentially, the process terminates when no vertices can move with positive gain. In parallel, race conditions can cause the process not to converge, and the process stops after a given number of iterations. That iterative optimization is the move phase, and once the move phase has completed, the graph is coarsened, and the process repeats to obtain hierarchical communities. The majority of the runtime of the Louvain method is spent on the calculation of affinity and community assignment in the first move phase. The challenging part to vectorize is the affinity calculation. The affinity of vertex u for a community is the sum of the edge weight that would become internal to the community if u joined that community. The affinity of vertex u is computed by listing its neighbors v and accumulating the weight of the edge uv to the affinity of the community of v. That right axis, indexed by the changing property of a neighbor, is unique to graph partitioning problems. It is found in graph coloring, graph partitioning, hypergraph partitioning, and community detection problems. It is not found in graph kernels like SPMV, BFS, or triangle counting. Once the affinity is computed, one needs to identify the best community assignment. That process goes about the way you would expect. To evaluate the performance of the vectorized Louvain method, we use the NetworkIt framework. NetworkIt implements the PLM algorithm for shared memory Louvain method. We perform slight adjustments to the code base to improve minor issues and make our experimental evaluation more fair. We call this version Modified PLM or MPLM. The core of the calculation is the affinity calculation. It is two nested loops going over the vertices u and its neighbors v to update the affinity of the community of v. The core problem in vectorizing this algorithm is to avoid concurrent accesses to affinity. We present two ways of vectorizing this algorithm. OVPL vectorizes the outer loop, while ONPL vectorizes the inner loop. To overcome the conflicts during the affinity calculation, a simple solution is to process multiple vertices at once in different SIMD lanes. One vertex per lane does that by processing vertices by blocks. It considers simultaneously the first neighbor of each vertex of the block. It requires to keep the affinity of all the vertices of the block in memory at once. For performance reasons, it is necessary to handle separately the cases where some vertices in the block no longer have neighbors, but some vertices still have some. Once written that way, the OVPL algorithm vectorizes gracefully, and the compiler generates the appropriate instructions with little programming effort. To make OVPL efficient, we need to reformat how the graph is represented in memory. First, processing simultaneously two neighboring vertices can cause convergence issues. So, we apply a graph coloring algorithm and group vertices per color. Then, each color class is sorted by degree to optimize vector utilization. Second, each block of vertices is represented contiguously in memory by interleaving the neighbor list of the vertices of the block. OVPL has a high memory requirement because it needs to keep many affinity data structures live simultaneously. One neighbor per lane solves the problem by processing a single vertex at a time, using the different SIMD lanes to process different neighbors. The challenge is that while different vertices are on different lanes, they could be part of the same community, which would cause unsafe memory accesses to the same location. Fundamentally, the operation is a reduced scatter. Fortunately, the recent AVX 512CD and AVX 512F instruction sets introduce the support necessary to solve that issue in two different ways. The first strategy works on vertices from different communities. For a set of neighbors, it loads the communities of these neighbors with the gather instruction. Then, it creates a mask by applying the AVX 512CD instruction, identifying conflicts on the community vector. The precise behavior of the instruction is complex, but the first occurrence of distinct values are set to 0. It enables to calculate the affinity contribution for the identified neighbors from different communities. The remaining neighbors are grouped together for further processing. This mechanism will give good results when the number of conflicts on neighbors is low. For instance, we apply this strategy in the initial move phase of the Louvain method. The second strategy is to process simultaneously all the neighbors from the same community. After gathering the communities, a simple test generates a mask for the first community. Then, a reduce add instruction from AVX 512F computes the contribution to that particular community. It then compresses the remaining vertices for further processing. This mechanism will perform well when the number of conflicts on the vector is high, which is expected to happen in community detection. We apply this strategy for all move phases after the first one. We perform all our experimental evaluation on graphs from the SNAP dataset. Modularity is one of the common metrics for community detection, and it is the one optimized explicitly by the Louvain method. We would not want to make the algorithm faster at the cost of generating worse communities. Experiments show that the vectorized algorithms do not significantly alter the quality of the communities generated. We evaluated experimentally the methods on the Skylake and Cascade Lake architectures against the MPLM baseline. The methods show good performance on both architectures for the move phase. ONPL outperforms NPLM by up to 2.5 times on Cascade Lake, with typical improvements between 10 and 30%. OVPL outperforms NPLM by up to 9 times on Cascade Lake, with improvements typically between 10 and 40%. OVPL showed great performance for the NLP KKT graph. It turned out that this performance is due to the regularity of degrees on that graph. We extracted more graphs from SNAP, where vertices have very regular degrees. They are shown here by size for both architectures. OVPL provides significant performance improvement once the graph is large enough if the degrees are fairly regular. Though, it should be noted that OVPL requires a significant preprocessing, which negates some of its benefits. We showed in this video how to use modern vector instructions to extract communities in a graph. While the relative improvements are modest, the algorithm is known to be particularly hard to accelerate using parallel computing. The methods we showed apply not only to the Louvre method, but to most graph partitioning problems. We believe that better compiler support could enable these reduced scatter patterns to be more widely used in practice. The improvement we present could be made generally available with little programmer effort.